Good morning, guys. Today we're going to continue on our notes with word problems involving exponential equations. This is part 2 of our notes from last lesson. And we're going to be dealing with continuous exponential growth and decay. So whenever we have growth and decay that's continuous over time, we're going to use a number that we've seen before, and this number is e. But again, the key word that we're looking at here is continuous, means that we're going to be using e. Okay, and if you remember, e is approximately 2.7. Okay, and so let's look at the equations here. If we look at these equations, we have growth on the left and decay on the right, and we have the representations of the variables here. N of t is the final amount, NO is the initial amount. Some textbooks call this, in math we call this N naught, but you can call it NO. It doesn't matter to me as long as you understand what that symbol represents. K is the growth constant, but K can also represent the decay constant depending on what we're working with, right? Are we working with something that's growing over time or something that's decaying over time? And T represents time. The difference between these two equations, if you notice, growth has a positive K and decay has a negative K. And continuing on here, it says, in writing exponential functions that involve e, we will be using a positive exponent to represent exponential growth and a negative exponent to represent exponential decay. Okay, so here we see that this exponent of x is positive, so it represents exponential growth, but also notice that the base, which in this case the base is e, the base is approximately equal to 2.7, which is greater than 1. And so this kind of correlates with the last lesson from last class, that if the base is greater than 1, then we have growth, right? Here, if you notice, the exponent is negative, so we're going to have exponential decay. But remember, if I have e to a negative, I can rewrite it as 1 over e. And 1 over e is approximately 0.4, and 0.4 is between 0 and 1. So from the last lesson, if the base is between 0 and 1, we have decay. And so we can conclude that if there is a negative exponent in an equation, we look at the base of the equation to determine if it's exponential growth or decay. Okay, so if there is a negative exponent, then we have to look at the base. If the base is greater than 1, then the situation stays as exponential decay. If the base is between 0 and 1, then it's exponential growth. And I'll show you how this plays out in the examples that follow. Okay, so let's take a look at the examples. Okay, so here we have examples 1. Oh, sorry about that. It should say 1 through 6. It says, state whether the function represents an exponential growth or exponential decay. So let's look at the exponent, right, and check to see what it is. Is it a positive or negative? Okay, so I'm going to put here the exponent. It's negative 8x, so we're going to say it's negative. And on the previous page, it says that if the exponent is negative, then we have to check the base to see if it's going to be exponential growth or decay. Okay, so if we look at the base for example 1, we see that the base is e. The base is equal to e, which is approximately, we said, 2.7, right? Which is greater than 1. So we're going to end up having exponential, what do you guys think? Exponential growth or decay? Correct, we're going to have exponential decay. Because remember we said that for this lesson we're looking at the exponent, and if it's negative we have decay, but we have to check the base and see if the base is greater than 1. Okay. Example 2. I notice that the exponent is negative. The base, on the other hand, the base is e, which is greater than 1. So it's the same situation as example 1. So again we have, conclusion is we have exponential decay. Example 3. We have an exponent that's, it's not negative this time, it's positive, right? The base is e again. E is greater than 1. So here's where things change. So here we're looking at the fact that the exponent is positive and the base is greater than 1, but because the exponent is positive, we have exponential growth. We have exponential growth. All right, example 4. I see the exponent and we have negative x. So I'm going to say, the exponent is negative. The base changes this time. The base is equal to 7, but it's greater than 1. It's still greater than 1. So it's the same situation as example 1 and example 2. So my conclusion is we have exponential decay. Example 5. We have an exponent that's positive, and we have a base of 7. So 7 is definitely greater than 1. So what did we do for example 3? Right? We said if the exponent is positive and the base is greater than 1, then we have exponential growth. So my conclusion for number 5 is exponential growth. All right, and then we have on example 6, I see that the exponent is negative, and the base, the base changes this time. The base is 1/8, which is a decimal, right? 1/8. over 8. That equals to 0.1125. And that number is it between, I think it is, between 0 and 1. So 0.125 is between 0 and 1. So here's when it changes. Here's the big change. If I have an exponent that's negative, but my base is a decimal, my base is between 0 and 1, I'm not going to have exponential decay. I'm going to have exponential growth. Okay, so I want you guys to remember that. This is the main part of the examples that I want you to get for this section. Is if my exponent is negative, but my base is a decimal that's between 0 and 1, then my conclusion is that we have an exponential growth function. Okay. Let's continue on here. 7 and 8. And again, I apologize for the numberings. It's not a big deal. So for examples 7 and 8, solve the following word problems. Okay, so 7 and 8 are going to be word problems. Let's see what they deal with, right? So let's read. For number 7, 100 grams of radium are stored in a container. Using the formula R equals A to the E of negative 0.0043 T, 0.00043 T, okay, so it's a really small number, where R represents the amount of radium remaining after T years, and A represents the original amount of radium. Find the following. How many grams of radium are remaining after 100 years? Round to the nearest gram. Okay. So, remember, we have 100 grams of radium are stored in a container. So that's, just to start off, that's the initial amount, the original amount. So if I'm going to use the formula, let me kind of zoom in here so I can write a little bit bigger. So if I'm going to use this formula, I need to figure out a couple of things, right? For example, 100 years, that's going to be T. What else? 100 grams of radium. It's going to be my A. And remember E is a number. It's 2.7. So the question is asking for how many grams of radium remaining. So it's asking for R. R is the value in question. Okay. So then let's substitute what we know. We're looking for R, but we know that A, that the original amount of radium that we have is, we have 100 grams of radium times E to the negative 0.00043 times how many years? Right, 100. And if we put this in our calculator, we get that R is approximately 95.7911, which it says round to the nearest gram, so to the nearest whole number. So my final answer is going to be that I'm going to be left with approximately 96. I'm going to round up. 96 grams of radium. So 4 grams less than when I started. So the number of grams in my container reduced, right? Because we were dealing with a decay equation. Our equation was dealing with decay. How do we know it's decay and not growth? Because remember, if the exponent is negative, we're dealing with decay. All right, let's look at 7b. 7b says, after how many years will only 5 grams of radium be present? Okay, so 5 grams, that's my R value. But it says, after how many years? So letter B is wondering about what T is going to equal to. But just remember, we're still dealing with the same problem, same number 7. So how many grams of radium did we start off with? 100 grams. So I don't want you to forget that. But we're still going to be using the same formula. R equals A times E to the negative 0.00043 times T. Okay, so let's plug in what we know. We know that R is 5, so I'm going to replace R with 5 equals 100 grams is what we're starting with, times E to the negative 0.00043 T. Okay, so let me go ahead and zoom in here a little bit. Okay, so we want to solve for T. The question is how many years? So I want to get T by itself. So my first step I would do is I would divide both sides by 100. These will cancel here. 5 over 100 reduces to 1 over 20. E is negative 0.00043T. And what we're going to do is we're going to use ln, because if you remember, whenever we're working with E, we're not going to use log this time, we're going to use ln. So we're going to write ln of 1 over 20 equals ln of E to the negative 0.00043 T. All right. In the next step, we're going to write, well, actually I'm going to copy this part of the problem. Actually, let me move this a little bit up. So copy the left side. We can move this exponent to the front. So I'm going to write it as negative 0.00043T times ln of E. And what we need to remember, or what I want you guys to remember, let me use a different color. Let me just use red. I want you to remember that this value remember that ln of E is equal to 1. ln of e is equal to 1. So this next step over here, just continue writing over here. I'm going to copy ln of 1 over 20 equals, if this is going to be 1, what's 1 times this? Just this, right? So it's going to be negative 0.00043t. And then how do I solve for t? What's the opposite of multiplying? Dividing. So I'm going to divide both sides by 0.0043 and negative 0.0043. So that's going to cause a cancellation here and here. And I'm going to get an answer for t. And you should get, if you put it in your calculators, you should get approximately 6,966.8192. But it says, in the instructions, it says rounds to the nearest year. So it's the nearest whole number. So because it's 0.8, I'm going to round this 6 up to 7. So I'm going to say approximately 6,967 years. That is a long time. It's a long time, right? All right. Let's do one more example. One more word problem. So you go and shift the page over here. Okay. So we have, okay, so now we're dealing with money. It says, Anaí, I'm sorry, I'm just trying to make sure it's level. Okay. Anaí deposits $1,000 into her account that pays 5% annual interest, compounded continuously. So keyword continuously. Remember we said if we use the word continuous, we're going to be using the number e. The formula a equals p times e to the rt gives the value of her investment, where p is the original amount of money she deposited, and r is the annual interest rate, and t is the time in years. Okay? Let's see the question. If Anaí leaves her money in her account, how much will she have at the end of 10 years? Okay, so far we know the time frame, t is 10 years. It says that p is the original amount deposited, and she deposited 1,000. And then it says that r is the annual interest rate, and it says here that the annual interest rate is 5%. Okay, and just a side note here, if r is 5%, that changes to a decimal of 0.05. Okay, so let me just copy the formula that we're going to be using. A equals p times e to the power of r times t. And so we're interested in how much money will she have? So how much will she have at the end of 10 years? So we're interested in looking for what a equals. Okay, so let's plug in everything that we know. we know that we know that P equals 1000 times E to the power of 0.05 times 10 years. Okay, and if we plug this into a calculator, actually let me do one more step, right? Because I can multiply these two, so I'm going to end up having 1000 times E to the 0.5. And then if I plug that into a calculator, I would get a dollar sign, $1,648.72. So she would have $1,648.72 in 10 years. All right. And let's look at the last one, letter B. It says, how long will it take? So here we're interested in how long will it take. So the question is asking about how much time will it take for her money to double. So for her money to double. So let's think about this for a little bit. If we're saying that her money's going to double, how much did she start off with? If we look at the top of the page, it said that she deposited 1,000. So if we're expecting that amount to double, what's $1,000 doubled? 2,000, right? $1,000 times 2 is 2,000. And we want to know how long will that take. Okay, so we're going to use the same formula. So let me go ahead and zoom into this problem. I also want to remind you guys, because I'm going to be zoomed in here, but P is the amount she deposited, right? Remember, she deposited 1,000, and R is the interest rate of 5%, but 5% changes to 0.05. Okay, so if I write out the formula, we have this. Let's substitute everything that we know. We have A is equal to 2,000 equals 1,000 times E to the 0.05 times T. Okay. So similarly to 7b, I want to get E by itself and eventually T by itself. So how do I get rid of the 1,000? Right, the opposite of multiplying is dividing. So I'm going to divide both sides by 1,000. 2,000 divided by 1,000 is 2. E to the 0.05 T. Then I'm going to use ln for both sides. ln. And then I'm going to bring the exponent to the front. So I'm going to copy again ln of 2, bring the exponent to the front times ln of E. But remember from the previous problem, let me use a different color here, that ln of E is equal to 1. So I'm going to have ln, bring down the ln of 2 and bring down 0.05 t. So this is going to, ln of e becomes 1, so 1 times 0.05 t is 0.05 t. And then to get rid of the 0.05, we divide both sides by 0.05. 0.05 and 0.05 will cancel there. And so we end up getting, if we plug this in a calculator, we end up getting that t is approximately 13.8629. And it says round to the nearest tenth of a year. So 0.8 is the 10th place, but because we have a 6 after the 8, the 6 is going to tell us to round to 0.9. So this 0.8 is going to change to 0.9. So my final answer is going to be approximately 13.9 years. Okay. Awesome. So I want to thank you again for joining me on this video lesson, and I hope it helps, and I hope it's able to explain to you what we wanted to make sure that you guys learn for this week. And just have a great day and continue to stay safe. And until next time, I hope you guys are safe and with your family. Goodbye.